Welcome everybody to another day of CS302 data structures. Today we're going to be talking about a very cool algorithm known as Dijkstra's shortest path. So I hope you all had a good long weekend with the holidays. And so you have been watching that other video with minimum spanning trees as well. So if you did and you saw Prim's algorithm, then Dijkstra is going to be very, very close to that minimum spanning tree algorithm. In fact, it's almost the same, but a little tweak. So if you haven't watched Prim's minimum spanning tree, then you actually can take Dijkstra's that I showed you today, and then pretty much you understand how Prims work. In fact, I would say that Prim plus a little extra is what Dijkstra is. And again, Prim is for the minimum spanning tree, which is when you're trying to find the graph with the least amount of edges that still keeps all of the nodes connected as they were initially, but you remove all of the extra weight so you keep it as light as possible. Basically, when you're trying to create a network with the least amount of wire possible based on the available connections that you have. And so Dijkstra's kind of changes the game a little bit. What you're trying to do is for a weighted graph, doesn't have to be directed, but you could in theory apply it to a directed graph, but really we are going to look at the undirected approach of, example of a graph. And what you're trying to do is say, okay, you have a couple of nodes. So here I have a little graph that I was actually doing just before the lecture started. So I might tweak around some of these edges just to make sure that you see interesting things happen here. Like maybe, I'm gonna actually make this be a 3. Yeah, okay. So here you have a graph, right? And I want you to think of each of these nodes as a computer. And what you're trying to do is you're trying to send a signal from computer 0 to maybe computer 5. And what you want to know is what the quickest or shortest path is between nodes 0 and 1. Or sorry, 0 and 5. So you're trying to go from here to here. Now, if I just, if this is the full size of the graph, you can pretty much quickly see that you could take that path, right? Because each of these weights are going to represent the time, let's say in seconds. Well, maybe better would be milliseconds. That seems more appropriate. So let's say each of these takes the time in milliseconds to reach that. And so if I take the path that I did there with the red line, I'm actually going from 0 to 3 and then from 2 to 5. And it's going to take a total of 3 milliseconds, right? Alternatively, suppose that this edge did not exist. Well, then what would be the quickest way to get there? Well, there's a lot of different options, but you have to go to the 1 first, because if you don't have this connection anymore, then your only choice is to go to the 1. From there, we have a weight that's missing. Let's go ahead and throw in, to make it interesting, a 10 there. Okay? Yeah. So if you have something like this, then if you're trying to go to the 5th node there, you can go this way, or you can go this way, or you could actually go this way as well. But it turns out that the fastest way to get there is going to be to take this route, because that takes 8 milliseconds. And if you took the other route, if you took this route, that would take 13 milliseconds. Or if you went this way, it would actually take even longer. It would take 14 milliseconds. So that will be the next best route. But, we actually have this route to be the ideal one. And so what this brings up is the fact that the harder or the bigger the graph is, the more connections there are, it's harder to figure that out. You have to manually go and check some paths. So one of the ways that you could do this with what would be a greedy approach would be to kind of find the depth first search traversals for this and just print them out. Print out all possible depth first search traversals, and as you do them, measure the weights. Which is kind of what I'm doing here when I said, okay, let me test this, let me test this, let me test this. But you could also potentially go and test the weird routes, like go there, or maybe like some this way. Actually, we didn't check this one. This could have been shorter potentially, but it wasn't. So you could do that, but that's going to be very, very, very time expensive to do, because now you're checking all of these different combinations, and it's not going to be very efficient. It's going to take a long time. So the way that Dijkstra basically said, we can improve this shortest path problem is he said, let's apply the concept of dynamic programming. Now, if you don't know what dynamic programming is the idea of remembering things. So when we go ahead and we do the tasks, we're doing things in the real world, we use our brains, right? Well, we should, or we hopefully do. And our brains have this capability of remembering things. And so if somebody tells you, okay, I need you to do a bunch of math computations, and they keep asking you what 5 times 10 is, there's a lot of computations, but 5 times 10 just keeps showing up, okay? Maybe it's like money conversion, and it's just the way things convert. Very quickly, you're going to memorize that 5 times 10 is 50. And so the next time they ask you, you don't need to do the math computation and manually go by hand and say, okay, what is 10 times 5, which is 50. In fact, that's why if when you were in elementary school, they taught you the multiplication tables to memorize them, because it's much faster to memorize some of these basic multiplications than to try to figure them out each time, right? So like if I said to you, what is 8 times 8, then you know that's 64 because you memorized it. But you could also figure it out by hand. You could be like, well, if 8 plus 8 is 16, and then plus 8, and then plus 8 again, and plus 8, and then eventually you get 8 of them, you get 64. So you could derive the solution, right? But if it would make your multiplying slower. And so what do? You memorize some of these more commonly used computations, right? And so that's kind of the same idea behind dynamic programming. With dynamic programming, what you want to do is, if you're doing something more than once, then why recompute it? Just remember it and then use that again. And so, for example, if you're trying to do Fibonacci sequence, okay? So Fibonacci sequence, that's a good one. Fibonacci sequence is the let me write it down. Good refresher for me too. Oh, hold on. Oh no. My tablet is doing strange things. I think it. Oh, hold on. Let's connect it. Unplug again. Okay, it was just the pencil was doing weird things. Okay, apologies for that. All right. So let's say that we're putting in Fibonacci. So Fibonacci is taking the previous number and the second previous number and adding them together. So you could say something like 1 and 1. And then 2, and then you take these two numbers and add them together, which you get a 3. 2 plus 3 is 5. 3 plus 5 is 8, and so on. So 8 plus 5 would be 13, and then the next one would be 21. Okay? So if I told you compute the next Fibonacci number, one way you could do it, like recursively, would be just like literally add, all of these numbers together to find out what this number is, and add them all together again to find out what this number is, and then finally add them together, right? However, that's pretty slow. What would you do? Do what I did right here. Just write them down, and then next time you get to compute a number, you have them ready to go, right? So what you do with something more complicated than an algorithm is you keep some sort of table. And you keep a table that tells you what the previous measurements were. And so that's exactly what you're going to do with Dijkstras. What we want to do with Dijkstras is, if we measure the shortest path between two spots, what you do is you basically remember that, put it down in this little table, and next time you got to figure out what the shortest path is between certain spots, you refer to that table. And then if you find a better path between them, all you do is you reference that table and then update it. So you're always keeping track of the shortest path between those spots. Now, if this doesn't make sense yet, that's okay. That's why we're going to spend an hour on this, because I'm gonna show it to you first, sort of the quick visual way, and then we're going to do it the more sort of algorithmic way, which would be how you would actually code it. And I think that's very important to see that as well, because there's a lot of hand waving that happens in the first way that I show it to you. Okay? But if you don't know dynamic programming, this is going to be the time for you to try it out and get your hands wet or feet wet. I don't know what the expression is. Hopefully the pen works, because it started glitching out. It wasn't glitching out earlier, but see that? It's interesting. Yeah, it's oh, I know why. The tip got loose. That, it has to be it. Yeah, that was it. Maybe I was fiddling with it and the tip got loose. But now we're okay. I do have the other pencil ready to go, because I remember that one thing in the actual in-person class where the pen just died out. Okay, so I went ahead and just created a little graph here, and what we're going to do is I'm going to show you how to do Dijkstra shortest path, and let's just go for it, and you'll see it. And again, what we're gonna get when Dijkstra finishes is actually, it's kind of cool. You don't just get the shortest path between the two nodes that you want. So like if you have a graph and you say like, I just want to know the shortest path between like 0 and 6, then to get your hands dirty. Is that it? But I've heard the one where it's like get your feet wet or something. I don't know. Maybe I am thinking of that. I don't know. But yeah. So Dijkstra doesn't just give you the shortest path between two nodes. It actually gives you the shortest path from a source node, which you get to pick. So let's say we're going to pick for that to be this as our source or start. And it actually gives you the shortest path for all the nodes. So that is cool. So even if you don't need it, it's cool. But also at the same time, it is a little expensive, but there's no choice. It's the only way that you can do this. Now, there's a lot of algorithms for shortest path. In fact, you're even going to go over Dijkstra again when you get to analysis of algorithms, which is CS 457, I think. They are going to go over 5 of them, like Bellman-4s, Dijkstra's. There is one limitation with Dijkstra's, which other ones don't have, and that is it only works for positive weight edges. So if you have 477, that's it, thank you. So if you have negative edges on your graph and edges of 0, I can't think of right now if it'll work or not, but that's kind of iffy. But if you have negative edges, then it will not work. The whole thing breaks down. Some algorithms do work at a certain cost in terms of time and space complexity. But yeah, so this is not the end of this shortest path problem. It's pretty popular actually out there. Okay, so let's do it. So what I'm going to do is I have my starting node, and what I'm going to do is I'm going to look at the edges. So the out degree, figure that out. So this is out degree of 2, and I'm going to look at those edges and pick the smallest one. Basically, that's pretty much what I'm going to do in the first thing. So in this case, 2 is smaller than 4. So I'm going to go ahead. Oh, hold on a second. Wait. Don't. Okay, I will correct myself on that. Apologies. So you don't pick the smallest weight yet. What you're going to do with this is you're going to look at both edges, and you're going to look at the nodes that they're connected to. So that would be in this case both 3 and 1. And then what you're going to do is you're going to keep track of 2 things on top of each edge, which I'm going to write here 2 numbers separated by a comma. The first of those is going to be the weight or the key. And what that is how much time, again, if you're thinking of this in milliseconds, or if not just the weight, what is the weight to get here from the source node, which again, we picked to be arbitrarily 0, but we could have picked anything else. So in this case, that is a weight of 2, okay? Or in the case of the 1, it is a weight of 4. The second thing that you're going to keep track of is the source node. The source node is basically the one before in this path. Now, right now, it's just going to be the actual source node, so it's going to be 0 for both. However, as you'll see later, like let's say we were computing this node here, and that node happened to be coming from here, then you're going to write down that source, okay? So it's going to be the source of where you came from. Now, it doesn't have to be the source of where you're starting. It's just sort of like it's the memory of the previous vertex in your path, okay? So again, this will make more sense once I go a little further. All right, so in fact, let me get rid of, can I get rid of the color that I printed here? Here, I'll just erase it and do it. So that you can get confused with that being colored, okay? So, proximate versus ultimate source, I don't know. I mean, you can use those terms, I suppose, if you feel comfortable with that. I don't know what the technical term is. By the way, Geeks for Geeks has a really good article on Dijkstra, which I was gonna link it on the YouTube description, which I will. But if you're watching live, you can open it there. And they have also sample code of that as well. And actually, we're going to do one of their examples when we do the other one, because I thought I'd just pick that because it was a nice little graph. So anyways, okay, now that you've done this, and I do have already written down here sort of the algorithm way of doing it, but again, we'll get there. So the next thing that you want to do is look at the vertices that you have visited already once, okay? And so far you've only visited the source vertex, okay? And you have a couple of other vertices that you have to remain to visit. In fact, technically speaking, you have pretty much everything but 0. However, all of these vertices right now, if you were to think about it, have a weight of infinity because you have not reached them at all. And if you have a weight of infinity, we figured that out when we're talking about adjacency matrices, that pretty much means that they are unreachable, okay? And right now we don't know if they are reachable, so we just say they're unreachable. So your choice comes down to basically 1 and 3. And what you're going to do is you're going to pick now the smallest weight of them. So in this case, the 2, 0 pair, okay? Why? Because this vertex has basically a weight of 2 associated with it. That's the key value of that. And this one has a key value of 4. So you go with the smallest one of the 2. You don't pick 0 because that has already kind of been marked as done. So we're going to put a little check mark next to it, actually, okay? Or you know what? We'll just use the coloring system for that. We'll color it, whatever this is, blue, purple, okay? And then this one, we're going to color blue or purple because we're visiting now, and when we finish with it, we'll be done with it, okay? So we never want to go back to those. Think about like breadth first search and how we didn't add, or depth first search, and how we didn't add things that were already visited to the queue or stack. Same thing here, exactly. We're not going to add things that we already marked as visited, but we only mark things as visited when we actually visit them. And right now we're only visiting 3. So I'm not just saying that you see them, but that you actually visit them, okay? Same thing. In fact, if I scroll up again, just to make sure that you guys remember this, we had our graph here for breadth first search. It's only when we marked in the visited array, which we will have 1, 2 for Dijkstra's, that we actually don't add things to the queue, or in our case, that we don't add them to the, or try to update the weights on them, okay? So, going back to that, in this case, we have nodes 3 and 0. And so we've selected 3 because, again, 2 smaller than 4. And what we're going to do now is we are going to look at the edges coming out of 3. And there's 3 of them. There's this one here. Here, let me use the laser pointer. There's this one, and there's this one. However, this one here, we're not going to care about because it's connected to a vertex that has been marked as visited. So we're not going to try to change 0 at all. We're going to let it be, okay? However, we do have vertexes 5 and 2 that do need to be updated because right now they just have sort of like infinity for this, and now it's no longer infinity. So what we're going to do here is we're not going to, this is where it changes for Prim. In Prim, what you would do here is I would put a 1 and then the source, which is 3. However, that's Prim right there. Prim's minimum spanning tree. However, for Dijkstra's, what I'm going to do there is I'm going to add the weight here with the weight of that edge, and then put that the addition of that. I was gonna say product, but product is multiplication. So in this case, you're gonna put 3. Okay, so you take 2 plus 1 and get 3. Again, this is the difference between Dijkstra and Prim. If you didn't watch the Prim video, then when you do, then this is pretty much what happens. It's just you don't add it. That's literally, I suppose you could say, you could take the source code for Prim and change it to Dijkstra, and minus a couple of tweaks maybe here and there. The big difference is just going to be that single addition there. That is going to make the world's difference, okay? And also what we are going to call the relaxation step, which you'll see in a minute here, okay? So we mark this sort of edge like that, and then we got to do the same thing for this one here. So that is going to be a 2, because we're coming in from the 3, plus this edge here, which is 3. So that is equal to 5. So we are going to put here a key of 5. We call it key, but just a weight. And then the source. The source is where it came from. And again, that's going to be 3, not 0, because we wanted the sources in like the last place that we visited before we got here, okay? And that helps us remember that is going to be the shortest path, actually. That's what's telling us that it's kind of like think of it like a treasure map, and you just get the X for the next spot, or in this case the previous spot, and then you got to go there and look at that treasure map, or like a scavenger hunt, I guess, where every spot you go, it tells you the next spot. It's kind of like that. You only know the previous spot, okay? And this is that's dynamic programming going at work here, actually, because you're remembering all of these things, and this is important, okay? All right, so we only marked 3 as visited because that's the only one that we've really handled. We have seen 5 and 2 and 1. We have seen those, but we have not visited them yet. We still got to go there. So now we're gonna pick from the ones that we have not visited the smallest weight. So right now this has infinity and this has infinity, so we're definitely not gonna pick that. And then here we have a 3, here we have a 5, and here we have a 4. So we are gonna pick the 3 because it's the smallest one. Okay, so now it comes a time where we actually mark, is this in color? I hope it is. we mark this as actually visited, okay? And so now we are going to look at all of the edges coming out of that are going to nodes that are not visited, which in this case is going to be that, that, and that, okay? Well, also, technically speaking, this one here again, but that is going to a node that we already visited, so we're not going to mess with that edge. Okay? So it doesn't really matter at this point which of the three you pick. You can go from smallest to highest in terms of weights, but it doesn't really matter, okay? So we're just going to go with the three to prove a point that we don't have to go in order of weights here. So we are going to go and look at this. So this is where it gets interesting, okay? By the way, oh snap, we lost the number that was here. This was a 3, right? It must have been a 3. Yeah, because 2 plus 3 was 5. Yeah, okay. So this is where things get kind of interesting, because this already has a value associated with it. It has a key of 5, right? And so we see that coming up from vertex 5, if we want to compute this key here, it would be 3 plus 3. That's equal to 6, right? But we currently have a 5 there. What this is telling us is that the path from the source, which is 0, all the way to 2 would take 6 milliseconds if we took the path that came from 5. However, when we see a 5 here and a 3, it's telling us that we already have another path that takes less time. It takes 5 milliseconds, but it comes from the 3 instead of the 5. In this case, we say, okay, we found another path, but it's not the best one. We actually have a better one already. So in this case, okay, don't update it. So you don't update. You also lost a 10 from 1 to 2. Did I from 1 to 2? Oh, yes, I did. Thank you. Thank you for that. I'm glad you guys remember that, because I would have not remembered that number. Okay, so that's interesting, because if we had found a better path, so let's say that instead of this 3, we had found actually like a 1. Okay, so maybe this was a 1 right here. If this was the case, then we would take 3 plus 1, we would get 4. And 4 is smaller than 5. So then what that would tell us is that we have found a better path. We have found a path that, sure, it takes more hops, but it's actually shorter in time. And that's what we cared about. And so in that case, we would update this value to a 4 and then put as a source of 5, because we're saying that's a better path, okay? But that did not happen, so we're not going to do it. And by the way, doing that update is what is known as the relaxation step. In fact, Dr. Gowali, who's in the CS department, says it really cool. He's like, then you relax. And it's really cool because it makes you remember that. So I love that. So I just remember that whenever I think of the relaxation step. You just relax, okay? Would it be 6? It would be 6 right now, as it is now. 3 plus 3 is 6. But 6 is bigger than 5. So in this case, we are looking for the shortest path, not the longest path. So we don't update, okay? All right. So I do hope that some paths do update in what we're about to do here. I didn't think, yeah, we are at least going to see one path update. Good, okay. So, all right, let's go ahead and take a look at the other 2 edges that we have. So let's just go ahead and pick this one. So this one's an easy one to do because in this case, we have this node, which has not been visited so far, and it has an infinity weight. So 3 plus 2, we're saying this 3 plus this 2 is equal to 5, and we're just going to put that this came from the 5. Okay, this is some weird thing where like the numbers are matching, but that's just coincidence. Okay, I literally picked this at random. Now we did have a question on the chat that said, what if 2 weights were equal? I'm glad you guys asked that, because I was going to tell you at some point if nobody did, but now you guys did. So that's kind of what that is telling us is that we have found 2 paths that take the same amount of time. In this case, it would be correct to change either or. Like you can pick either or. But I would just recommend you leave it be so that it's less work. But what this tells you, like the meta of this in terms of the algorithm, what it tells you is that there are 2 solutions or more, I suppose, to this problem of finding the shortest path. It's telling me that this node has 2 shortest paths, assuming that state, of course. We might get updated and we might find an even shorter path at the end of the day. But so far, it's just telling us that there's multiple solutions. And all that Dijkstra tells us is a solution, not all solutions. So in that case, we can simply just accept. If we wanted like some sort of exhaustive solution, then we'd have to do the really slow method of just that first searching everything and finding all possible combinations. So yes, but you could always You can still actually use Dijkstra to find multiple solutions. You would just have to, at this point, generate two entire, like, alternate solutions. Just two complete different graphs, basically. But yeah, so you don't have to update, basically. That's the easy short answer for you. But I'm glad you asked that. Okay. Finally, we got this weight to update. So this weight right here is also easy to update because 6 is right now infinity. So we can just go ahead and say 8, comma, and then the source, which is 5. All right. So that takes care of all of the edges that are coming out of 5. So it's been marked as visited. So now the next thing we're going to do is we have to pick from the remaining vertices. So what vertex do I pick next? It's a little bit of a trick question maybe. But yeah, so which vertex should I pick next? Actually, not a trick question. I lied. But yeah, you guys tell me. What vertex should I pick next? So I have an options of 1, 2, 4, and 6. 1, that is indeed correct. Why 1? Because 1 is the one with the smallest weight. Okay? So wouldn't 5 to 6 be 11? Oh, yes, I apologize for that. I am glad you guys caught that, actually. Yes, so I switched into Prim mode for some reason. So yes, actually, 5 to 6 is the addition of 3 plus 8, which is 11. So I'm very glad you guys caught that. That means maybe I did that intentionally to see if you guys were awake. That's the lame excuse everybody says. But yes, I'm glad you guys caught that. Okay, perfect. So anyways, going back to vertex 1 here. Vertex 1 is the only choice we have, actually, because that's the smallest weight. The reason I said a trick question for a second is because I actually saw the 2 5s. So I saw that vertices 2 and 4 had a 5 weight to it, and I didn't see the 4, so I was like, trick question because it could be either or. But in this case, there's no trick to that. There's only one that can be chosen because 4 is smaller than 5, 5, and I guess 11. Okay, so from there, we're going to look at what it's connected to. So we have this edge to deal with. We also have this edge to deal with. And technically, we have this edge as well, but we don't look at that one because it's going to a vertex that has already been marked as visited. Okay, so let's just pick one of the two. Let's go with this one. So in this one, we're saying 4 plus 10, which is 14. Is that smaller than 5? No, it's not. So we don't do any relaxations. We don't do anything. We just keep going. Okay, we look at this one. We got 4 plus 6, which is equal to 10. Is 10 smaller than 5? No. In this case, we also don't do anything. So here's a vertex where we visited it. We checked the edges. There were no updates. We just move on. So we like those. Those are fast and easy, right? Okay, so now we're in the situation where we have the 2 5s. So here it doesn't really matter which one of the two you pick, basically, because at the end of the day, they have the same weight. So it will not change your algorithm at all. It doesn't mean. It also does not mean that there's multiple short paths in this scenario. So just pick one. Let's go ahead and pick this one because actually it turns out that there's nothing that's going to get updated at that point. All of the vertices that it's connected to, the 3 edges, they're all marked as visited. So no updates happen there. That's pretty nice. Okay. Now the next one we have to pick is the other 5. So this is where we actually will see something interesting happen because this has 3 edges that we need to check. However, 2 of those are going to already visited vertices, so we don't need to worry about that. But we do need to worry about this edge. And guess what with this edge? With this edge, we're saying 5 plus 1, which is equal to 6. And we're saying that 6 is smaller than 11. And because 6 is smaller than 11, that means that we have found a new shortest path to get to vertex 6. So right now, before, the shortest path to vertex 6 was basically going from here to here, and then, whoa, that's interesting. And then from here to here, and then there. Well, we just found a better path. We have found a path that is coming from vertex 4. So we're going to go ahead and update that. So we're going to basically get rid of this old thing. So just bam, throw it away. Gone. And we're going to put our newest shortest path, which is going to be 6, comma, and then the source, which is 4. Okay? Let me just get rid of that. And so this is what is known as the relaxation or relax, okay? And why it's called relax is because I suppose it's connecting it to a chiller, I don't know, a shorter path. Yeah, just whatever mental explanation you can go for that, but it's called the relaxation step, okay? So yes, that's it. So now we have found the shortest path to all of these nodes. So how do you read this? That's another tricky thing. Okay, the way you read this is if you're trying to find the shortest path from 0 to, let's say, 4, okay? If you want to go from 0 to 4, actually maybe 6, because we just did that one that's furthest away. You don't actually start from 0. What you do is you go to the end. So in this case, you go to 6. And when you're there, what you do is you follow the roadmap. So from here, it says go to 4. You don't need to worry about looking at the weights, but just go to this. Although this will tell you how long it's going to take for you to get to 0. So it says each estimated wait time is 6 milliseconds. And how to get there, you got to go to 4. So I go to 4. Okay, estimated wait time now is 5 milliseconds. How do I get next? Oh, I got to go to 5. So I go here. Oh, sorry. It's hard to not look where I'm going. Okay, there we go. All right, I get here. Now it says I am only 3 milliseconds away. And it's almost like we're on the subway here. And then here we have the next path to go. So go there. Now we're only 2 milliseconds away, and the next one is actually where we want to go. So that's cool. So next stop. Bam. We have arrived to our source. And that is indeed the shortest path. You cannot find another path in this graph that would take you quicker from 6 to 0 unless you use some time travel mechanism. Okay? So another example, let's say we want to go this one. Oh, sorry. Let's say we want to find the shortest path here. Okay? So this one doesn't look right. Why is it? Oh, never mind. It does look right. Okay. So in this case, you know, this is a path, but it's not the shortest path. The shortest path here is just to go to 3. So we go to 3, and then from 2 to 0. As you can see, that is indeed a weight of 5, which is what this tells us. So this tells us both the shortest path and how long it's going to take in terms of time. Well, again, I keep saying time, but this is weight based. Okay. It might also be how much energy you need to get there, or distance, and it doesn't have to be a specific measurement. It's just a weight, okay? It's a value. So it could be the number of steps, anything. Okay, so this is like Dijkstra in a sort of basic way of visualizing and understanding it. Now all that matters is basically converting this into actual code, which the way we do that is we're going to make it more sort of algorithmic, okay? But does anybody have any questions about the basic idea of Dijkstra? So what I did here is I went ahead and sort of wrote the pseudo algorithm code for how to actually do Dijkstra, okay? And so this is pretty much what I've been following along when I was doing the algorithm, but this is more of like a formalized way of writing it. So let me go ahead and translate this to you to plain English, I suppose. So, and if you have any questions, just drop them in the comments, okay? So for all, this is the for all symbol. And so for all V that belong to G, and this is V stands for the vertex. So for all vertex that belong to this graph, where V dot visited is not equal to true, V dot visited is going to be our visited array. So maybe I should have shown you this this little table here before I do that. Okay, so we got some good questions. So if we were asked to do this in the exam, how do we show the steps? Well, you're going to show this algorithmic way that I'm about to show you. So what you'll do is you'll draw this little grid table, and you will fill it as you will see in a minute here. So that would be the best way for you to show it, because you could show it this way, the way we did it, but you'd have to do a lot of drawing. This is a lot easier because it's a table, so you can like copy and paste and then just update the values. It'll be much easier for you. That's what I encourage you to do. Wonder how somebody would come up with this on their own. Pretty cool. You know, Dijkstra actually came up with a lot of interesting things. It wasn't just the shortest path that he did. Dijkstra's like an OG cool guy. Maybe I should link to the Wikipedia of him. But he was Dutch, by the way, if you didn't guess by the name. And is he still alive? No, he's not alive. That's very sad. Hold on a second. Is this yeah, there we go. Okay. I was looking for the other Wikipedia, but this works too. But I'm actually trying to find out what year he did this. Maybe if I just look at this Dijkstra shortest path Wikipedia, I will be able to find it. Let's see, what year? 1956. So it was conceived by Dijkstra, Edgar Dijkstra, in 1956 and published 3 years later. It's interesting that it took him that long to publish. So publication does take time, but 3 years is, maybe he was just formalizing it too. Maybe he didn't realize what he'd done too. That is very possible. You can go ahead and read the Wikipedia. There's some history about the algorithm there. But yeah, I mean, this is within not my lifetime, but like my parents' lifetime, I suppose. But what I'm saying is within, it's not something that was discovered like 500 years ago. It's not like calculus or something. Okay, this is like pretty recent stuff if you think about it. So, and some of the other algorithms for shortest path are pretty recent as well. So yeah, and then again, this is more math when he did it than computer science, but a lot of this math has translated to us in CS, so that's why he's more of like a math person. But no, he's regarded as a computer scientist as well. So yeah, he was a theoretical physicist by training. So there you go. Okay, so anyways, I mean, when you know the algorithm, you're like, wow, this is obvious and easy. But coming up with it, I guess, is not so obvious and easy. So anyway. So what this is saying is, you got to remember the notation we talked about. This is saying for all vertices in the graph. So for all vertices in the graph, okay. And so this is our graph, and we have the number of all the vertices here, and then the keys is going to be the weights that we're going to keep track of. The parent is going to be the previous node that is coming in the path, and then this is our visited Boolean array. Okay. So we're saying for all vertices in the graph, we have not visited yet, so v visited is not equal to true, and that is when we check mark, it means it's true. You go ahead and pick the smallest remaining key. So pick the smallest number in this key row here. And then for that key, so this is what you're gonna do for that key. Now we're looking at the edges. So for all the edges that belong to this specific key, which we are going to refer to as u, okay? We're gonna refer to that as or actually, is this belonging to yeah? So this must be is belonging to you. So I wrote this 6 months ago, so kind of rusty. So for all edges that belong to this specific key that we picked, okay? For this vertex that we picked, so we're looking at the vertex that has the smallest weight, okay? So this is when we're picking the smallest one. So for that one, what we're gonna do is we are going to take the weight of that, so the key of that, and we're gonna add it to the distance from that one to the vertex that we're looking at, okay? And so if that value is basically smaller than the key, and that vertex is marked as not visited, so again, we don't wanna look at edges that are connecting our vertex to a vertex that has been already marked as visited. We're only looking at the new vertices that we haven't marked as visited, okay? So if we find a value that's smaller, that's when we want to do an update, okay? And then, so the way we do the update is we are going to take the value of the key that we're looking at, and we're going to add that to the weight of this path right here that we're looking at. So this is the previous value plus that path, the edge's value, and then update the parent as well, because we are updating that vertex. And then when you're done, so this is actually outside of the entire loop, this whole thing is we mark this u as visited, okay? So let me go ahead and say that again. So we're looking at all of the vertex in the graph that are not visited yet, okay? And then we will mark those visited. So we're gonna do this for all graphs, for all vertices. We're gonna pick the smallest one that has the smallest key. We're gonna call that vertex u, okay? Then we're looking at all the edges of that vertex u. And we're saying that is the vertex u value plus the weight of the previous vertex to that vertex. If that is smaller than what we currently have in the vertex, then we're going to update it by updating the weight and the parent, so to the new parent that's faster, okay? That's what's happening, all right? So hopefully that makes sense, but if not, again, I'm going to go ahead and do it, okay? You could actually translate this pretty much as is two single lines of code and get this algorithm working. Like this would be a for loop up here. Well, if you know range-based for loops, then this will be a range-based for loop for all of the vertices, and then this would also be a little for loop in here for all of the edges of a specific vertex that you picked. And then this is just a single if statement. This is a single assignment. This is a little function that you can make to pull the specific edge that you're looking at, or you can just, you could use that as the iterator of this loop. And then this is a single assignment. And this is important. I should really move this because this might be misleading, but this is actually outside of this inner for loop. It's inside the outer for loop, but it's outside the inner one. So it would be kind of lined up there. Okay. It's not inside of here. You only mark something as visited when you've checked all of these. Okay. All right. So let's go ahead and do this for this graph. Okay. And this graph is coming from Geeks for Geeks, so you can also see how they do it there as well. But we're gonna do it. I don't have the solution in front of me actually, so we're just doing it naturally, I suppose. Okay. So in fact, no, I'm gonna stick with picking the same source node they pick, because then I know for sure there will be relaxation steps. Because it might be like this. This one was random, and we actually only saw one relaxation. So while it was nice that we saw the relaxation, it'd be better if we saw more of them. So that's why I'm picking something that I know will for sure have relaxation. Because at the end of the day, it's good to relax, right? So yeah. Okay. So we have a little source there, and so what we're gonna do for the parent of the source is you don't really have a parent of it, so we just kind of put a little dash, and also mark it as visited. In fact, I forgot to actually uncheck all of these. Let's uncheck all of these since we're gonna say they're not visited. Okay. So you can set them to false. I'm just gonna leave blank to represent false. Okay. But I am gonna mark the first vertex as visited because we are just landing there right now because this is where we're starting. Technically speaking, I don't have it here written, but all of these would be initialized to infinity, okay? So maybe I'll throw it in, but I'm gonna erase it. So they're all initialized to infinity, except for the source vertex, which you are going to just initialize to 0, just because, I mean, you're starting there, so you're already there. The parents are all just kind of not set to anything because they don't have a parent, so don't set them to anything. Just hardcode some value that means it's not there. Whatever you want, just an invalid vertex value, whatever. Just make sure that they're not set to anything, okay? And then you got your visited array set to false for everything but the starting vertex. I might have to shrink this a little bit so I can fit it. There we go. Okay. So we're ready to go. This, of course, is just, I mean, you can make this like an array or an object. I would make it like an array of an object that contains 4 variables, which are actually 3 variables: key, parent, and visited, and then just use the index of the actual object to be the vertex if you're storing this in a computer. Okay. All right. So we are going to start by looking at all of the edges that are connected to the source vertex, which in this case is 0. And this, I'm going to put a little arrow to remind us where we're currently working at right now. Okay. So what I'm going to do, and this is the part where I'm going to pick the smallest remaining key, which of course is the source, because that's the only one that's set to 0 and not infinity. And now we're going to go ahead and say for all edges that belong to that. All edges that belong to that are only 2 of them. It's actually just this one and this one. Okay. So for those 2, we're going to go ahead and do that. So we're going to say if essentially the weight that we have here, which is infinity, is smaller than the weight that we have coming from this vertex, which in this case is going to be nothing, 0 plus 4. So 0 plus 4 is smaller than infinity. So we are going to enter the if statement. And so now we're going to go ahead and update the values at 1. So it is no longer infinity. It is now going to be 0 plus 4, which is equal to 4. And the parent is no longer going to be just a random thing. It's going to be set to 0. Okay? No mark nothing as visited right now. We don't. And next, we're going to look at the next edge. We have the edge going to vertex 7. Vertex 7 is currently set at infinity. 0 plus 8 is smaller than infinity. Therefore, we are going to update it as well. We are going to set this to 8. Technically speaking, I suppose that would be relaxation, but I don't think the first time you do it is called relaxation. So yeah. And then again, the source is going to be right now vertex 0. After that, you have basically finished the 2 vertices or the 2 edges here. So you can go ahead and then mark 0 as visited, which we already kind of did, but whatever. Okay? Technically, you would do it at the end. I just like doing it at the beginning because otherwise I'll forget. So it doesn't really matter if you want to move this statement up here, as long as you know what it means and why it's there. Okay, so here's the interesting thing. Now, what you have in this table is you know how to get to vertex 1 and 7, okay? This is the dynamic programming part. You remember this, so you don't have to recompute it every single time. Suppose that you did not keep the key row. Suppose you only kept the parent row, okay? If you only kept the parent row and you were trying to compute, let's say, the next vertex that we're going to see here, you would have to recompute the key row for that specific path. That's extra computations that are unnecessary. This is what we're solving by using the programming. Okay, I'll bring that back when I have more written in here. But I just I want you to keep aware of that as we do this. Okay. So, anyways, now what we're gonna do is we are back to the outer for loop of this, and we're gonna pick the smallest remaining key that is not marked as visited. So that pretty much leaves us with these. We have a 4, we have infinities, we have an 8, and we have infinities. So we're gonna pick the 4 because it's the smallest one. So we're gonna work with this. I know we are gonna mark it as visited at the end, but I really don't want to forget that, so I'm gonna put the check mark. Okay. So yeah, all right. So and also let me move my little arrow so I know that I'm working there. Okay, so what we're gonna do is we're gonna look at for all edges coming out of that. So we got 3 edges. We have edges of the 4, the 11, and the 8. But here's the thing. Remember this little part of the if statement. In fact, maybe I should maybe if you want to make this a little extra efficient, I would move this if statement, like I would flip the logic around slightly so that you can check whether it's visited first, so you can take advantage of short circuit evaluation for that. Okay, a little extra efficiency would be achieved that way. But anyways, if you do it that way, then you see that you know this marks as visited. So because v.visited is equal to true in the case of 0, so we're not going to go ahead and update that. That basically means that no matter what is here, we're not entering that if statement. Okay. For the other parts though, that is not the case with the v as visited being marked as true. So we are going to be looking at those two. So we got 8 and 11, and in this case, let's go ahead and handle the 8 one first. So the 8 one's going to vertex 2, which is currently infinity. 8 is of course smaller than infinity, so we are going to update that, and we are also going to set the parent to whatever that came from. So that happened to come from oh shoot, sorry, my bad. I keep thinking of Prim. You're not just going to put an 8 there. You're going to put the addition of the source that you just came from. So in this case, sorry, I'm going yeah. I was jumping a little bit ahead. Yes, that's what I'm getting to. So you're gonna put the source of that. So you're gonna actually take this value here, which is going to be the equivalent of u.key, and then you're gonna add that to v.key, which would be 8 in this case. So you are indeed going to put 12, and then you're gonna put the source as a 1. Okay? So that is basically the equivalent of you having here a 4, 1, and then taking this and then saying 12, 1. Okay, so that's basically what we're doing over there. All right, so from there we are going to look at the other edge that is connected to that. So that would be this one here, and so this one is more interesting because we basically are going to see if 4 plus 11, which is 15, if that is smaller than the 8. That of course is not the case, so we are not going to go and update it. But here's the thing, this is the dynamic programming part. The fact that we know that this is an 8 is because we have that stored. If we didn't have the key stored and we just had the parent and we said that, oh, well, there's a path from 7 to 0, you would have to recompute that path as well to be able to do this. So the fact that we remember that that takes a time of 8 is allowing us to compute this faster, is allowing us to basically achieve this in v squared time, I believe, thanks to dynamic programming. Okay? So, yep, that pretty much takes care of 1. So we mark it as visited and we're good to go. So now we got a 12 and we got an 8 in here. So we are going to go ahead and pick the 8, which is vertex 7. Okay? So vertex 7 has 4 edges to look at. We have basically this, 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 and this. However, these 2 are going to nodes that have already been marked as visited, so we are not going to mess with them. We're just going to go and look at these 2. Okay? Fortunately, 8 and 6 are both not visited, so this is going to be a quick update and set them to the source. Make sure we don't screw this up this time. We want to add the numbers. We don't just want to put them in. So in the case of 6, we're going to take the number that we currently have here and then add that to this weight value. So that is going to be 8 plus 1. So 8 plus 1 is 9 when this is coming from 7. And in the case of 8, we have 8 plus 7, and that's what we're going to put there. So 8 plus 7 is 15. And then, of course, that is also coming from 7. Okay? That takes care of all of the edges coming out of 7. So we are going to mark that as visited. Okay? So now we've got 12, 9, and 15. 9 is the smallest one of them. So we are going to go with that one. Okay, so that is vertex 6. So vertex 6 has 3 edges coming out of it. We have this one, and this one. Okay? However, of those edges, the one going into vertex 7 has already been marked as visited because vertex 7 is marked as visited, so we are not going to worry about that one. So really, we only have to worry about 2 edges, the one going from 6 to 8 and then from 6 to 5. So 6 to 8 is actually a rather interesting one because that is basically saying 9 plus 6, which is equal to 15. Okay? But we already have 15 in the vertex. So this is one example like you guys were asking, where the number that of the way to get to that vertex is the same that we already have there. So in this case, we don't need to update. What this again is telling us is that there may be two scenarios that have the shortest path in this graph, like 2 possible solutions. It's not always the case, because this could get updated. Like there could be a new short path that just solves this. In fact, that is going to happen here, that there's going to be a new shorter path to 8. So it doesn't necessarily mean there's 2 solutions, but it might. If this vertex was never updated again, then yes, that would mean that, but not always. Okay? But anyways, for now, what it all means is we're not going to update it because we already have 15. We're going to say whatever, keep the original one. Don't do extra work. It's as fast as this, so just let it be. In fact, if you saw it first, there could be a chance that it means that you actually got there with less hops. So there's a certain, you could potentially say that might be good. I don't know. It doesn't have to be always the case though. So no, don't actually go with that. Because you could actually, yeah, forget that part. Okay. So that takes care of the 6 to 8 right here. So now we're going to look at this edge here. So 5 is infinity, so that's an easy one. We're just going to take whatever 6 has, which is 9, add 2 to that, and then just throw that in there, and then put the source as 6. Okay? You're always copying the source of what the little arrow is pointing to. That's why I have that little arrow, which is very convenient. You just basically, whatever that's pointing to is we're going to put here when you're updating that. Again, this is easier coded than explained. Explained, the other method is so much easier. This one's so easy to mess up, but coded, this just works beautifully. Okay, so that's it. That's all the updating that we got to do. We are going to mark that as done. So now we got a couple of choices. We have infinity, 11, and 15. So we're going to go with 11. All right, welcome to 5. 5 has 4 edges to work with, of which one of them has already been marked as visited. So really, we're going to deal with 3 edges. Okay? Visited means all edges from the vertex have been checked, right? No. Visited means that we selected that vertex to go to and then check the edges out of it. That's all it means. So how do you pick a vertex to visit? You pick the smallest weight of them. So like right now we picked 5 because 11 was smaller than the remainder ones, which are 12, infinity, infinity, and 15. That is what, when you finish dealing with all the edges there, then you mark it as visited, okay? So it's not whether the edges have been exhausted. It's about, I mean, in theory, after they've been exhausted, you probably won't need to update it anyways, but algorithmically, you want to visit it anyways to make sure that that's the case, okay? So yes, only mark things as visited when you're actually there. That's fine, no problem. Okay, so, all right, we're looking at 5 and we got 3 edges to deal with. So let's just go ahead and deal with the ones that we know, to make things quicker. Let's deal with that edge first, because that one's I know, 4 is infinity and so is 3. So those are definitely going to be updated. So that's an easy one. So 3 and 4. So in the case of 4, we are going to take the 11 that we have here and we're going to add that to 10. So that is going to be a really big number, 21 actually. I mean, at least compared to the other numbers. And then in the case of 3, we're going to take 11 and we're going to add 14 to it. So that's an even bigger one. That's 25, right? So 11 plus 14 is 25. Yep. Okay. So big numbers there. Big numbers. That's good because hopefully those get relaxed. We haven't really seen much relaxing going on. Okay. One more edge. Don't forget this one. So that edge right there is going to be 11 plus 4, which is 15. But we have a 12 there. So 15 is not smaller than 12. It is greater than 12. So in that case, there's no relaxation required for that. So no change happens in vertex 2. Okay, we're done with that. So that's pretty cool. We no longer have infinity in any of the key values of any of the vertex. What this tells us actually is that the graph is at least weakly connected, I suppose. But actually, well, it's an undirected graph. So really, we don't really think about strongly and weakly connected. What it tells us in short is that all the graphs are reachable by the source node. So they're connected in some way or form. Now it's just a matter of finding out what the shortest path is to that. But at least we know. We can be like, yay, we can reach everything. It's a good sign, I guess. If you're Cox Internet, that's pretty much as far as you go. You're like, well, they're connected. Who cares if they're fast or slow, right? So, yeah. Okay. So, all right. We got 12, 25, 21, and 15. So 12 is the smallest one. So that's where we're going to go. And now we're going to mark that as visited when we finish working with it. But that's only when we mark it visited again, okay? So in the case of vertex 2, we got 4 edges coming out of it. Of those 4 edges, we have the edge going to vertex 1, but vertex 1's marked as visited, so we don't need to worry about that one. We also have an edge going to vertex 5, but that has already marked as visited, so we don't need to worry about that one. We do have an edge going to vertex 3 and 8, both of which have not been marked as visited. The actual vertex itself is not marked as visited, so we are going to do that. Oh yeah, thank you. I apologize. I forgot to add the parenthood of that. Thank you for that catch. So, yes. Okay. So, all right. So let's go ahead and update those weights. So let us start with the 8, okay? So that's this edge right here. So what we're saying is we have 12 plus 2, and we're checking if that is smaller than what we currently have in 3, which is 25. Well, 14 is indeed smaller than 25. So that means that we are going to relax. So we are going to replace the 25, or sorry, not the 25. The I mixed the numbers up a little bit here. Sorry, I was looking at 3 and then at 2. Let me redo that again. Apologies for that. So we got the 2, okay? So we are looking at the edge. I guess we're going to look at the edge of here, hold on. Undo. Okay. So let's go ahead and go with this edge, just because I somehow want to do that one first, okay? So we're saying 12 plus 7, okay? So 12 plus 7 is 19, all right? So 19, is that smaller than what we have in 3? What we have in 3 is 25. So that is indeed smaller than this, okay? That is smaller than this. So therefore, we are going to update this with the new smaller one, which is 19. And we're going to change the parent because it's no longer 5. That's no longer the fastest route. The fastest route is whatever we're pointing to, which is the 2. Okay? So that is relaxation. We have done relaxation on that. Basically means we found a better path than we had found previously. Okay? This is this other one here. So in that one over there, we are saying that 12 plus 2, which is 14, is that smaller than what we have in 8. Well, we have a 15 in 8, so 14 is smaller by a little bit, but it is smaller. So we're going to take this 15 and we're going to make it 14. And now that means that 7 is not how we got there. It's not the fastest one anymore. It's 2. So we also update that. That's another relaxation that's happening. What we're saying is we found, again, another path that is faster than what we previously had. And then we can mark this as done. And yes, for the test, you'll have a smaller graph. But more importantly, if you were doing it in person, what I do is I just print out these boxes that are empty with all the vertices like this, so you can just fill them out and do them. But in the computer, it's actually not as bad because you can copy and paste, so you don't have to keep redrawing this. But yes, this is a very meticulous thing to do. As you can see, it's very easy to screw things up with numbers. So, but we're almost done. Okay, so we got 3 vertices left to do, 19, 21, and 14. So 14 is the smallest one. As you can see, that actually used to be 15, but it became 14. So it would have still been the smallest one, but that could have changed things. All right, so 8 is going to be a situation where it has 3 vertices, but 7, 2, and 6 are all visited. So there will be no updates whatsoever. So we can just mark it as done. Okay? Now we got 19 and 21. 19 is smaller, so that means we're vertex 3. Vertex 3 has 3 edges coming out of it. We got 2, 5, and 4. 2 is visited, 5 is visited, so only 4 is not visited. So this is the only edge that we really have to worry about. So in this case, we are going to say that 19 plus 9, which is equal to 28, is that smaller than 21? The answer is no, it is not smaller than, so there will be no relaxations, so no updates happen there. That's the only edge we have to worry about, so we marked it as visited. Technically speaking, I do believe that when you have everything but 1, you're actually done. If I recall correctly, the algorithm is a shortcut. If you only have one vertex left to visit, then you're actually done. But hey, if you want to play it safe, just check it anyways. Where at 4 we have 2 vertices, they're all visited, and you can see why that's the case, right? Actually, that's not as I thought it was figured out, but I just realized it's not. Because think about it, you got a bunch of vertices, and it means that if you're looking at a vertex that's not done, but everything else in the graph is done, it means that whatever it's connected to is going to be marked as done, right? So then that kind of tells you that, oh well, if everything is marked as done, then everything must be done, right? So that actually makes good sense. That could be a good exam question, actually. Like, why is it that we can stop Dijkstras when we only have 1 vertex left to visit? Yeah, I might actually put that on the test. If I remember it, it'll be on the test. Because, yeah. Okay, so Excel would work for this, sure, but I don't feel comfortable as a CS person using Excel, especially as a person that knows databases, because I feel like that's like blasphemous to use Excel in computer science. I feel like we should be doing like Matplotlib or something if you want to do graphs. But yeah, no, you can talk. I can see, and I did see somebody in the midterm, probably you, that used Excel to show some output or something. Somebody showed me Excel. I think it was you, but I don't know if it was an exam. It might have been a worksheet. But yeah, no, I know what you're saying, and sure, go for it. I'm a Paint person, so I like to use Paint for these kind of things. But anyways, that's Dijkstra's. And I know you only saw 2 examples, but that's because they take a long time. But I can just do more examples at this point. But I think that you guys got it. The thing about to be careful of, like you saw there, is make sure you add the numbers together. If you don't add them together, you're doing Prim's minimum spanning tree at that point. Okay, that's the only difference. In fact, just because we did have that as a pre-recorded lecture for the minimum spanning trees, let me make sure that we're all on the same page of what our minimum spanning tree is. if we were trying to calculate the minimum spanning tree of this, what we would do is, in Kruskal's method, you sort them by weights, and then you basically remove the heaviest ones until you lose connections to something. So you would be like, well, this is the heaviest, so we get rid of that edge. The next heaviest is the 11, so we get rid of that edge. The next heaviest is the 10, so we can get rid of that edge. Next heaviest is a 9, but if we remove that, you know, if you think about this in sets, then we basically will lose connection to 4, so we cannot remove that. So we go for the next one. The next one is 8. We can definitely remove that. Oh, but here's the thing. There's 2 8s. So that means that there's 2 solutions to this minimum spanning tree. So we're going to pick one of them. But just know that there's 2 solutions in this scenario. From there, we cannot remove the other 8. So we go to the 7s. We can't remove this 7, but we can definitely remove this 7. And then we go to 6, but we can't. Yeah, we can still remove this 6. And then 5, nothing. 4, we cannot remove this one, and we cannot remove this one. 3, there's no 3s. 2s, we cannot remove that, 1, there's not. So that will be the minimum spanning tree of this graph. Bam. That's Kruskal's. Prim's is the more fancy one, where you essentially do what we just did with Dijkstra, which is like, I'm going to do it really fast and probably screw up because I'm going to do it fast, but I like to show you one example of that. So what you're going to do for that is basically the same thing. So you start out, put both weights to it. So you say 4. The first step is always going to be the same in both Dijkstra and Kruskal, actually, because you're starting from the source. And then make sure you set your parent to 0s. And then from there, pick the smallest one. So go with the 4. Okay, so basically we're working with the 1 because this is 4. Mark that as visited before you forget. And then go ahead and add the 8 and the 11 edge. So that means that this here becomes an 8. And the 7 is already an 11. So we're not going to update it. But that's the thing here. You see that? I'm putting in an 8 there instead of a 12 in. Come on. It switched to typing mode. There we go. In Prim's minimum spanning tree algorithm. Okay, this is Kruskal's over here. Make that nicer. It's kind of nasty. Kruskal's. Okay. So Prim. See, be careful in the test. Do not get them mixed up. Okay. I do give you the choice. I believe in the test. Prim or Kruskal's. It's your choice which one you want to do. But if you do Prim's, just make sure you don't screw up between that and Dijkstra's. Okay, because there you're not adding them. That's the only difference with Prim. Everything else will be literally the same. So I guess in a way, if you know Dijkstra, then you know Prim, and vice versa. As long as you know that very important difference that you're not adding the weights, you're just throwing them in if they're small. So, anyways, in this case, we are done with that. So we go ahead and pick the smallest one. So we have the 8. So just go with one of the 8. Again, this shows you again that there's 2 solutions to this minimum spanning tree, at least 2 solutions. So in that case, with the 2. We've got 3 with a 7. Again, you're not adding at this point. And this goes to 2. And then we've the 5 with a 4. And then you have the 8 with a 2. And then you don't check the 1 because that's already marked as visited. So you still don't do the mark as visited thing. Okay? And then somehow, too, I forgot to put the source of that as well. But that was the source of 1. And, yeah, okay. All right. And then from there, you got a bunch of them. Go for this one because it's the smallest number. Vertex 8. For vertex 8, you have the 2, but that's marked as visited, so you don't worry about that one. So you only got these 2 other ones. Let's put the 6 in there. Again, you only put a 6. And then you put 8 as the source. And then for the 7, 7 is smaller than 8. So you are going to change this to say 7 there. and then as the source you're going to put 8. So see, it's the same thing as Dijkstra's, but you don't do the addition, which is a whole world of difference. Okay? I don't know if you want me to continue to the end of this example, but that's pretty much how you do Prim's minimum spanning tree. Okay, which is the video that I said you should watch over the holiday break, and that you want to use this method for when you're actually doing the assignment with the Edge of Tomorrow assignment. Okay. So, does anybody have any questions overall? Protein data in Excel, that's funny. If not, I'll just keep writing here the solution to this while I wait for questions. So this is a 10 with a source of 5. And then 14 does not get updated. 2 does get updated though. Oh no, that's marked as visited, so we don't update that. 6 does get updated. From 6 here becomes a 2. And this becomes a source of 5 because that's smaller. And I think I'm done with that one. Again, I'm rushing, so I might screw it up. And we got 7, 10, 2, and 7. So we'll go with that one. 6 to 5 is a 2, but that's marked as visited, so we don't touch it. 8 is marked as visited. 7 is not marked as visited, and we did find something smaller, so that one will get updated. This becomes a 1, and then that becomes source of 6. Okay, that handles that. 2 left, 3 left. Well, 2 technically, because we don't need to do the last one, but 7 has a connection with 1, which we took care of. That's 11, which is bigger yet. So 1 no need to worry about, 0 no need to worry about, 8 not need to worry about, 6 not need to worry about. So that one's just nothing happens. And then we've got this one here, 3. 3 has, the only place it can go is 4. So we are going to update this because 10, 9 is smaller than 10. Change this to 3. Mark it as done, and yet again the same thing as before. You don't need to look at that last vertex. Okay. So if you wanted to generate the minimum spanning tree from this, then you basically connect the parents. You basically draw the lines from here to here, here to here, here to here, here to here, here. Do that, and then you make it. So essentially, how to do this in an easy way. Let's just redraw the graph with the dots just in the right order. So like that, that. Okay. So this is 0, 1, 2, 3, 4, 5, 6, 7, and then 8. Okay. So basically draw 8 to 2. That's coming from here. 8 to 2. 8 to 2 there. So that, then 7 to 6, so 7 to 6 there, then 6 to 5, 6 to 5 there, 5 to 2, 5 to 2 there, and then 4 to 3, 4 to 3 is there. Again, what I'm doing is I'm looking at this and this and just drawing all of these, okay? So 4 to 3, 3 to 2, 3 to 2, 2 to 1, 2 to 1, 1 to 0, 1 to 0, 0 to 0, which you don't do anything for that. And so there you go. We actually have a different minimum spanning tree than before. So you can see that was the other alternative, right? Because we picked the 8s that were the same. See how you could have picked either this or this, so we actually ended up with different solutions. But again, that's because of that division that we had, like division, not like math, but like split. Okay. And if you want to add the weights to these, it's just the numbers that were in between. So like 8 to 2, this is a weight of 2. 7 to 6, it's a weight of 1. 6 to 5 is a weight of 2. 5 to 2 is a weight of 4. 4 to 3 is a weight of 9. 3 to 2 is a weight of 7. 2 to 1 is a weight of 8. 1 to 0 is a weight of 4. Okay? Which is pretty much what you have. Now, it's a little messy. I know. I just do it quickly just to show you that it actually does work, the algorithm. But yeah, that's the last algorithm that you're going to learn in this class. So we got good questions here. So there's 3 types of minimum spanning trees. No. Dijkstra's shortest path is to solve the shortest path problem. Minimum spanning trees is a completely different problem that just happens to have a solution that's very, very close to Dijkstra's. Like literally Dijkstra just took 2 numbers and flipped them kind of thing. In fact, I don't know who came out first, if Kruskal or Dijkstra. Or sorry, Kruskal or Prim came out first. I'm going to guess Prim's modified Dijkstra's, but I don't know. I don't want to claim something I'm not sure about. So all I'm saying is that minimum spanning trees is that topic that there was the videos to watch on. So I just want to make sure you guys watch them. That's why I thought I'd actually do it in live to make sure you know. Because those are ones that I recorded last semester. Your final is on the 7th. Let me see if that's correct. Yes, your final is on the 7th from like 1 to 5, but you have it based on your section. So 1 to 3 or 2 to 5. So you can choose either or. So you have that gap up here to start it in between them as well. Kruskal, it's Kruskal, not Kruskal. So if you did Kruskal's first, then we can verify the answer on Prim. You can verify your answer with Prim if you did Kruskal's, sure. But Dijkstra is a completely different algorithm. It's just that the algorithms like are very similar, but what they're trying to do is different. The fact that you're not doing that little addition, you know, when I'm building a minimum spanning tree, I'm not trying to find the shortest path. Like if I show you the minimum spanning tree that I made here, this is not the shortest path between 1 and 2. 1 and 2 here is like wrapping all the way around that. 1 and 2 there is just a single hop, and that was actually a weight of 8. That's actually a faster way there. But all it's saying is that this is the minimum spanning tree of a graph is telling you of all of the edges you have, which of them can you remove without losing connectivity between two vertices that were already connected. It's the okay, we got to do some budget cuts situation, so we got to take as many edges as we can without losing connection to a certain client. And which one should we take out? The highest weights one, because those are the most expensive. So like if I have a very simple graph, if I have this graph right here, okay, and I have, come on, I have this, okay, and I have a graph, this is 10, and this is 20, this is 1 and 2. And I tell you, okay, actually, maybe flip, sure, leave it like that. And I tell you, okay, we need to cut as much cable as we can from this plan. This is like some architect or engineer tells me like, hey, this is the layout cable that we're going to put in for this new area of residence for Cox Internet or something. And so flat out, the engineer gives you this and you're like, yo, each of these is miles of cable that we have planned. And I tell them, wait a second. If I go ahead and take out this 20 right here, I still got all the nodes connected to each other. Sure, this has to go a long path, but so what? It's still going to keep connected. So then what do? They get rid of it because it's pointless to have that. It's very expensive. Now, in this case, it actually doesn't affect it because it is faster to go this way. But suppose that this was a 10. Or not even a 10. Let's say this was 11. Okay? In this case, these could connect in 11 milliseconds, let's say. But now, because of the budget cuts, they get rid of that. And they can still connect. But now it's going to take them 13 milliseconds. So they got a little short end of the deal. But the company saved 13 miles of cable, let's say. Okay? Now, could they have instead said, hey, we're going to remove this one? Sure. But you're still spending more money on cable. That's unnecessary. Or worse yet, let's say they just flat out say we're going to remove this 1 mile of cable. Now, that's very inefficient. Because you could have removed the 11 miles or the 10 miles, but you chose the 1 mile. Now you can't remove anything else because you lose connectivity. So minimum spanning tree is finding the ideal scenario of what you can remove from a graph, what edges you can remove, the most expensive ones, so that you can have the minimum spanning tree, which is the graph with the least amount of weight overall that's still connected, as the original one was. And if you actually do the math and you were to add all of the weights together of the remaining graphs, so just flat out like add the weights, you would find that the weight of this is the same as the weight of the other one that we made, which is going to be some number that's as low as possible. And no other combination of weights of edges you could have will give you a bigger number. So that's kind of what that means. So Is there going to be a graph worksheet? No, there's not, because we're close to the final, so it's just going to be in the final kind of thing. Why are negative weights a problem? So, okay, so negative weights are a problem because of how the relaxation step works in Dijkstra. So it's not made to have negative weights, and it actually screws things up because relaxation like messes up. So the algorithm just breaks, like flat out just breaks. So there are algorithms that can handle negative weights, but they come at a cost, and that is time. They take longer to do, or they take more memory. There's a lot of different pros and cons. I recommend if you want to look, I believe Bellman-Ford can deal with negative weights. Let me check very fast. There's also, let's see, Bellman-Ford. Oh, Bellman-Ford versus Dijkstra. Yeah, it can indeed, it can detect negative cycles in the graph. The only difference, okay, here we go. The only difference between the two is that Bellman-Ford is also capable of handling negative weights, where Dijkstra can only handle positive. So yeah, Bellman-Ford will be your choice. I'll put the name here in case you're curious. Bellman-Ford. I want to make sure there's no weird spellings. So that is also another algorithm, and you'll learn about it in 477. It'd be cool if I taught that class, because I really want to teach it, because I could make the videos on that. Are the 30 minutes cooldowns for the extra credit attendance on Twitch intended? I think it's not cooldown. It's more like people sent too many already. But that's okay. You can just do it on Wednesday. So just go ahead and do it on Wednesday. But I'll try to get rid of the cooldowns for Wednesday. Okay. More questions, or did I miss anybody's question? Like I said, the game plan for Wednesday is going to be for me to review for the exam. But also, I like to spend maybe the first 20 minutes or so talking about algorithms in general. And maybe P versus NP. I have a lecture on this that was like an hour, 20-minute long. I can't do that this time around because we're limited on time, which is okay. You'll learn about that again in 477. But I would like to introduce it. So what I'll probably do is I'll just open the notes from that lecture and just talk about some things. And if you want to know more about it, or you're interested, you can watch last semester's lecture. And then that way, you know, we'll cut off at 20 minutes and then just do review for the rest. I do need you guys to come with questions of what you want me to review, though. Otherwise, I mean, I can do like an ABL. I can do another one of these, but I can't do every single subject, which is why I prefer you guys tell me what you want me to review. Is it going to be a longer lecture for the review? I mean, I could in theory, because I don't have anything after this. I'm done for the day, and it's Wednesday, which means I'm pretty much done for the week, quote unquote. For at least for teaching, that is. So I could in theory go a little longer if you guys want me to. I'm fine with that. I'll eat a bigger breakfast. On Wednesday, I will make smaller point rewards. I mean, I have right now the 100 pointers, but I will do maybe like 50 pointers. No, don't send me any screenshots. I'd rather you guys do it on Wednesday. This is the only time we had an issue with it, though, to be honest. But don't worry. We'll figure it out on Wednesday. I'll try to remove the cooldowns or whatever. Maybe I'll do that at the end of class or something. But that's funny, isn't it? Hey, I guess that's motivation to show up early. But yeah, we'll figure it out. Don't worry. All right, then. It's like pre-ordering a graphics card. You need to code yourself a redeem bot so that the moment I go online, you redeem before other people do. So it's a challenge. You know, you gotta work for that extra credit by coding a redeem bot that just like instantly activates it. I mean, I can see here the stack of people. Here's a warning though. For those of you that did redeem the extra credit for watching the lecture live, claim it today. Like, send me a message because I have to clear the queue. And if people don't send me a message, then I'll just reject the points and you'll have to redeem it again. So make sure you send me that because I have people sometimes wait 2 days and then maybe that like clogs the queue. I don't know. But yes, we'll figure it out. Don't worry, your points will not be gone. We will figure it out. Worst case scenario, we will do the. You can do the screenshots on Wednesday or something. Oh, is that a thing? Did you? Oh, yeah, that would make sense. The redeem bot will be a bannable feature, but yeah, that's funny. I bet you there's something already out like that though. That would make sense because people probably do that for Twitch. I'm not a big Twitch person, but I do know a little bit about how the channel pointings work. So, yeah. All right then. So come with questions, all right? Make sure you come with questions because otherwise you will not take as much advantage of the review as possible. So I'll see you guys. Thank you all for coming here to watch, and stay safe out there. Maybe. Hey, we will just go to a different streaming service to teach class. Yes, Wednesday is review. Plus 20 minutes of interesting stuff at the beginning. So, and plus extra time for redemption. Out of stock. We'll figure it out on Wednesday, don't worry. But I have to I can't do it now because even if I try to change it, it forces you to restart the stream. So, can't do anything now. So just Wednesday, we'll figure it out. All right. Have a good night, everybody.